So a linear regression, if you see a simple linear regression, so simple as the term tells you that it has got only one predictor variable. So now you know what is a predictor variable and what is a, so there are two types of variable. We did that in the first workshop also. There is something known as the dependent variable and there is something known as the independent variable. So dependent variable, we make some prediction about that dependent variable based on predictor variable. So that predictor variable or independent variable, these two are same. So because here in simple linear regression, as this term suggests simple, that means there is only one independent variable or there is only one predictor variable. The second is linear, because in the linear regression, like can you recall that correlation concept where we plotted the scatter plot and we learned that how for the correlation to apply, we need a linear relationship between the two continuous variable. We could do that with the help of a chart builder and a scatter plot. We'll do that again today because for linearity, we need that scatter plot. So if the behavior of one variable is linearly associated with the other one, then only we can apply the linear regression. So this is the second thing. And the third term is the regression. So because regression means that with the use of a mathematical formula, we predict. That's why it's a linear relation and that equation is of a linear relationship. So that's we mean by a simple linear regression. Why simple? Because there is only one independent variable. Why linear? Because if it is not linear, we cannot use this simple linear regression. And regression, because there is a regression equation, and based on that equation, we predict the value of the dependent variable with respect to the independent variable. So are you clear in the beginning about this simple linear regression? Don't go, get get this fear of this regression, because it may sound a bit fearful, but it is as simple as the concepts which you learned in the basic, because it's a stepwise process. And if you follow that step, definitely it will lead you in the formation of the various prediction equation and model. So the linear regression, it's a statistical tool which describes the relationship between a dependent variable and an independent variable. And remember, we are predicting the dependent variable based on a single independent variable. So here the independent variable is single. The second, it explains the impact of changes in the dependent variable by a change in the independent variable. And then the third is the response variable is the dependent variable. So it explains the change in the response variable and it does the prediction that how much the change in the independent variable lead to the change in the dependent variable. So now you can see here there are two requirements. We need one continuous outcome variable, that is the y, and we need one continuous predictor variable, that is x. So now you have to answer me that in the chat box. Like, first, my objective is I want to predict body mass index from observed abdominal circumference. So please write in the chat box what is the predictor variable in this case and what is the outcome variable. Outcome variable is the dependent variable, and remember, predictor is the independent variable based or by taking the value of that. So one by one, we will go one by one. So which is the, so predictor is abdominal. Pavan, Meera, they are writing. Shruti, outcome is the BMI. Predictor is abdominal. Okay, Aditi, Viraval, Neeraj, Pankaj, Divendu. Yes. So I think all of you are right that abdominal circumference, it is the independent variable, and based on that, Dr. Mukta, Pankaj, Prabhakar, yes, BMI is the outcome because we want to predict the BMI based on the abdominal circumference. Now the second objective is you have to predict the height of sons based on the height of father. Now, what is a predictor variable here? So Veeraval is writing the height of father. It's the predictor. No. Predictor is we have to predict the height of sons. So yes, the predictor variable is, you are right, it is the height of father, because height of father is you can remember that the predictor variable is the independent variable. So the height of father will be the predictor variable and outcome variable will be the height of son. Yes, yes. So all of you are right. Outcome is the height of sons. Now the third question is doses of medication and hours of relief. What is the predictor variable in this case and what is the outcome variable? Doses of medication. So Shruti is writing predictor is doses and hours of relief is the outcome variable. Okay, so doses is predictor. So you are right. Dose of medication is a predictor variable and hours of relief, maybe for pain or any symptom, that is the outcome variable. And the fourth one is the attendance, percentage, and marks. So what is the predictor variable in this case? So percentage marks is predictor, yes. So Neeraj just did like P and O. That is also a good way. So you can write P for predictor and O for. So predictor is attendance and the outcome is the marks. So by seeing these continuous variable, and you can see all these variables are continuous in nature, whether it is abdominal circumference, whether it is body mass index, height of the father, height of the son, doses of the medicine, hours of relief, attendance. So attendance here, attendance will be measured as percentage and marks obtained. So all the variables, either the predictor or the outcome, both the variables are continuous in nature. So this is the equation of simple linear regression. Remember in the first slide we have dissected these three terms: simple, linear, and regression. Why simple? Because in all this example, you can see that there is only one predictor variable and there is only one outcome variable. So outcome variable in all these cases will be one only, but there could be a mix of many variables in the predicted. But we called in the beginning, it is simple. That means we will use only one predictor variable in the simple linear regression. And the third term we use the regression. So what is this regression? So basically regression is, if you can recall your maths, 9th, 10th, even if you don't recall, just remember it, that this regression, this is expressed whenever there is a line, this equation, this y is represented as beta 0 plus beta 1 multiplied by that x, where x is the predictor variable and y is the outcome variable, plus errors or residual. I will explain these things one by one. Please, by seeing this equation, don't think that it is going to be very heavy to you, right? Yes. So like Neeraj is writing, predictor is x, yes, and outcome is y. So this is there because we need to make a equation in the last, at the last, when we will learn the interpretation. So this y is the your outcome variable, beta 0 is the intercept, and this beta 1 is the intercept of the predictor variable plus errors or residual. This will be the formula for the describing a bivariate relationship using a straight line, right? So are you clear up till this point? So if you can see this graph, you can see there are two axes, x-axis and y-axis. There is a line, and then you can see these blue dots. So can you see these blue dots? They are lying here and there is a distance perpendicular. I mean, there's a distance which we are trying to measure. So this is the residual. I'll show you in the next slide what is a residual, because in these terms, you know what is y, you know what is x. These intercepts we will calculate from the linear regression. And this, now I will introduce you with a new concept, that is the residual. It is called as error, but we will, for all practical, yes, Neeraj, I am explaining you this error and residual. So I will explain you what is this residual, because in all these linear and logistic regression, we will be talking of residuals, which we did not talk in the earlier sessions. So this is a new concept of residual. It is very much similar to the, can you recall the chi-square? There we learned about the expected and observed. Remember, we try seeing the difference between expected and observed. Larger the difference, greater the significance of the chi-square. So it is somehow, if you can correlate, I'll explain you what is this residual. So before I explain you the concept of residual, just hold on for 2 or 3 minutes. After this slide, that concept of residual will come. So there are some underlying assumptions to apply these chi-square tests. Sorry, these linear regression. So now what are these underlying assumptions? So the first assumption is that we know that that dependent variable should be continuous. The independent variable should be continuous. So this we can know by the type of research question. There are 4 other assumptions which we test on the SPSS statistics. So before applying SPSS statistics, we cannot test for those assumptions, and it is necessary to report for these assumptions when you are writing your statistical analysis. So the third assumption is there should be linear relationship between the two variables, that we did in the correlation also. There should be no significant outlier. So there we used to do, if you can recall the previous session, we used to use the option of explore. And in explore, we could, that in normality and in that box plot, we could see the outlier. Remember, more than 1.5 box length was a normal outlier, and more than 3 box plot was a extreme outlier. But here in this case, the SPSS gives you a case-wise diagnostic table which tells you the outlier. So we will see all this. I have just summarized it here. Then we have read about the independence of observation previously also. So here we will talk of independence of observation in terms of residual. I'll tell you what these are. I'll explain all these concepts slowly one by one, and then the data needs to show homoscedasticity. This homoscedasticity is very much similar to that concept of variance. Remember that we did that in ANOVA, in one-way ANOVA, where we used to use the Levine statistics for the seeing the this variance. So this homoscedasticity is very much similar to that variance. Now, what are these? I will explain you one by one. So if you see this graph, this is the first one. You can see this explains you a linear relationship because you can draw a line. But if you see this is a type of parabola, and this is also not a linear relationship. So both this graph and this graph, this, if the pattern is like this is non-linear. So the second is, you can see the linear and non-linear relationship. So the first one is the linear, and the second and third is non-linear. So can you see this? So now, if you go to the next slide, so here you will see the concept of residual. So can you see this is the graph plot of a BMI cholesterol. So BMI is the cholesterol is the dependent variable. So can you see this? These two variable. So now you can see there is a straight line. And if you see this straight line, there are many blue dots. So can you see these blue dots? So this straight line, this is the predicted value of cholesterol based on BMI value. And these dots which you can see, these are the observed value. Because this regression, what it does, it draws a line, which is the most fitted line based on the predicted value. So there will be two things. Based on some equation, you will predict that the value of cholesterol will be this much with the corresponding value of BMI. That will be predicted value. But there will be some actual value or the observed value also. So these dots are the observed value, and this line is the predicted line or the predicted or the fitted line, right? So now you have to see the distance between these two. Actually, it is the difference between the actual or the observed value and the predicted value. Now, in this example, you can see there are two cases. This is the case number 91. So the case number 91, if you see its observed value. So what is the observed value? If you see this 8 here, it is somewhat 7.89. The observed value of this case number 91. If you see the predicted value, you draw a line connecting that line should be a vertical line connecting that value, and the other point should be on that regression line or the most fitted value. So you can see from the y-axis that the predicted value from the equation is 5.79. Can you see this? So if I show you here, so are you clear how this 5.79 has come? If not, then I'll explain once again, because you need to understand. This has come by this. Can you see? So this, if I draw a straight line, sorry, it is a rectangle, but if you can see that it is the corresponding value here in the y-axis. So if I draw a line from this predicted value, if I draw a line from this to the y-axis, then this is the predicted value from the equation. And the actual value of this is the 7.89. So difference between the observed and predicted value. So you deduct this predicted value from the observed, and this error in prediction, it is the residual. This is the 2.18. Is it clear to everyone? For this case number 91, if anyone, how do we know that the line is a predicted value? Yes, because the regression equation and the fitted line, it is the line of the predicted value. This we know by our theory that this line, it draws, the computer software draws this line. I will tell you to draw this. You have to give a command, that best fitted line, and then that software gives you that line. Actually, this you don't have to do. This all calculation, that software, SPSS does it in the background. It is just to make you understand. I'm explaining you. Otherwise, these things you don't have to do. That SPSS does it for us. Is it clear to you, Viraval? Okay, so he is okay. Now, any one of you who has got any problem with this case number 91, I'll repeat again once. Rubina is writing difference between unstandardized and... Don't ask, Rubina, please wait for these terms to appear. Yes, here we are writing that unstandardized. Unstandardized means that we are not converting, because this residual will be different for if we are taking many values, like you will see in the multiple linear. Here there is only one variable, so you can make it standardized. But when there are many variables, all the variables for comparison, you standardized it. So you standardize it in terms of the standard deviation. So if you take the difference between the mean residual and individual residual, and express it with the standard deviation. It is known as the standardized. Standardized means if the other variable here is along with BMI, it is the systolic blood pressure. There are many more variables. Then by standardizing, you can compare the residuals of each other. The unstandardized, you cannot compare with the two variable because the unit will be different. Like here you can see it is 2.18. If it is, kindly repeat the difference between standardized and unstandardized. Okay, so standardized, unstandardized residual is like there will be many residual out of this. Like, so if you take a mean of all these residuals, is it okay? And you deduct that mean residual with that predicted value and divide it by the standard deviation, then it is the standard residual. Like, is it okay to you? So like if I cannot write it here, like if I take 3 example, suppose a residual of 2, residual of 3 and residual of 4, right? So in this case, what we will do, you can take the mean of these through, it will give you some value, maybe that 3. So with this 3, and you take the predicted value from the equation. So from this mean residual, the actual observed one, the mean, this difference of residual, if you take the mean of this and you deduct the predicted value, then it will give, divided with the standard deviation, it will give you the standardized residual. And the unstandardized is the raw. It is just the difference between the predicted and the observed. Because the unstandardized, the unit will be different. So like if the variable, question. Okay, so Neeraj, did you understand this concept? Like if I use rupees and dollar, if there are 2 different units, maybe someone is measuring in rupees, someone is explaining in dollar, or if there are many variables where the unit one is the millimole, the other one is expressed as milligram percentage. So yes, so Riya is writing observed minus mean residual and divided by standard deviation. So yes, mean, it's the observed residual, that's the predicted one. So predicted minus mean is the, observed is not. So it's a predicted minus mean divided by standard deviation is standardized residual. And basically to compare it, we do it like this. And unstandardized it like, okay, so you have understood. So unstandardized it it's the raw one. Yes, chat idhar dikha do to easy rahega. Yes. So is it clear to everyone what is standardized and what is standardized? There will be one more concept, studentized. So I'll explain you that also. But right now I'm restricting myself because there is a studentized residual also. So, but I'm not going into the detail because that we will learn in the multiple linear regression, right? So now is it clear to everyone what is this residual? Just first learn this unstandardized residual because we are not explaining it we are not converting it in the standardized one. It is just the unstandardized residual. So unstandardized residual case number 91. Now you can see the case number 2. So can you see the case number 2 here? The difference, the observed value is 4.8 and the predicted value from the equation is 5.35. So can you see here, this value of predicted, if you draw a line connecting this point and y-axis, then this is 5.35. And then the actual value is 5.557. So, sorry, actual value is 4.8. So all the variable dots which are below this line, it will have a negative residual because this observed minus predicted, it will be in negative, right? So, but it doesn't matter, the sign doesn't matter, the positive and negative. It just tells you the difference between the observed and predicted the value. That's how we call it as a residual. Okay. So, did you understand this concept of residual? And then this unstandardized and standardized residual. Is it clear to all of you?
Ma'am, why have we just taken case number 91 and case number 2? I mean, this is just to explain, right?
Yes, yes. You can similar concept will be applied to all the points which you can see here. This SPSS statistics is doing this work in the background for all the data set, for all the individual case which you enter, right?
Okay.
It is just to show you the one positive and one negative. You may take any value and you can calculate. It is just to show you the difference between the predicted and observed, gives you the value of residual, and there will be some value of residual for all the cases. You know, there will be few cases where the residual might be 0. That you can see there are few cases which are lying exactly on this line. Can you see this line? There are few dots which are exactly on this fitted line. So there the predicted and actual both will be equal. That's why the value of residual will be 0. Do you get
where is this predicted actually coming from?
Okay, so this predicted is based on your equation, based on your statistics, because that there are few examples which will show you from where this predicted is coming. So based on this equation, statistical equation, and your statistical subjects, this computer predicts, because there is a probability. Basically, it's the calculation of probabilities. See, so
if I understand correctly,
is calculated based on event. Yes.
So if I understand it correctly, it is almost analogous to the mean and error. The way we calculate the error, right? So we deduct,
or what?
Yeah, we deduct it from mean. So for mean value plus or minus, we calculate the error. Is it similar to?
To some extent, yes, you can say, but the applicability is a bit different here. Because here in the equation also, if you see, we will see it later on, that this we don't include it actually in the equation, that error. In the initial one,
if cholesterol was the response variable,
yes,
then as the software predicted according to the BMI, that so the predicted value is the one that the software predicted would have been according to BMI, which is the predictor variable, and the observed value is the actual value that we got.
Yes, which you enter. Yes,
which we enter.
You must have taken some value. Yes.
Okay.
Actually, this software based on statistical calculation, based on assumption, predicts something, and then you see how much it is different from the actual value. So ideally, all the residual should have been 0, right?
Yes,
if your prediction was so good, then ideally there shouldn't have been any residual. But actually, in practice, this doesn't work like this. We cannot predict something to that 100%. Remember. So that's why there is a bit deviation, and these residuals measure those deviations. And that's why we accept these residuals, that if its value is within 3 standard deviation, within 2 standard deviation, within 2.5 standard deviation, that will be acceptable to us. So the cutoff depends. We will see in the commands that the cutoffs are different, and we can change the cutoffs also, right? So and based on this only, this defines the outlier. So if the value, this residual value, if it is very high, the difference, then you may remove this because it can affect your model, right? But if again, like we studied for the outlier, that if the numbers are very less as compared to your total sample size, then you may decide to keep it. Main is to report it. The similar concept which we have read initially.
Dr. Shruti?
Okay, ma'am.
Hello?
Yes.
Listen, suppose after examination of a student, you just ask how much marks you are expecting. That is predicted. The student will say, in paper 1, I am expecting 80 marks. Some will say 76, some will say 41, some will say 99. Okay, this is predicted value, predicted by student. Now result will come. It may happen that I said I am expecting getting 80 marks in paper 1, but I got 76. The residual is 4 for that student. Okay,
I got it.
In that way, you can calculate the residual. Ideally, it should be that every student should have very near prediction. But if I am predicting that I will get 99, I am getting 50. It's too much difference in prediction. That's why my prediction is not good. So residual should be as less as possible.
Yes, yes, exactly.
The equation wonderful. If it is residual, if the total sum of residual is very high, that means your equation is not working perfectly in prediction.
Right, got it.
And
Thank you.
ideal situation, it will never happen, because there are many techniques, because there is a diversity in the measurement tool, there are the people, they behave differently. That's why we take this cutoff value, that if my residual will be within ±3 standard deviation, I'll take this. And if it will be outside, if you want your model to be very precise, you can keep your residual cutoff up till 1 or up till 2. But generally, it is recommended that you keep it either from 2 to 3, 2, 2.5 or 3. That we will see while we put the command in the SPSS. So Neeraj, I think you asked one more question. Can I see the chat box? Neeraj ne kuch likha tha. Kindly repeat the difference between. So Neeraj, did you get this question? Or anybody else who would like?
No, I was looking at the importance.
To repeat the concept of this. Importance of residual.
You have already got explained that basically to see who are the outliers and whether to include or not. So I think that is the implication of looking at residuals.
Yes, and no, here also that, when you check for the normality, here you don't, what we did in the previous sessions, that we were doing the analysis on the raw data. Raw data means we were not doing because we did not do the predictions before. In the predictions, there will be a gap between the predicted value and the actual value. So here you will see that we have to test the normality also of this residual. And this we will do by this. So by residual, we do 3 things basically. We check the variance of this residual, we check the normality of this residual, and we do the outlier work of the residuals. So there are 3 functions of this residual. Is it clear?
And
so
what is the implication of each? Like why we check variance? So what is the implication of variance, outliers, and the third thing you said is?
Yes, there are 3. So if you can hold for few, because there is a separate slide everywhere, because in the one slide, then I'll have to repeat all the concept. So I think just hold for few, 10, 20 minutes, and then you will get all these concepts, because we are going slowly, so that maybe for you it is easy. There are many more participants who may find that, everything is getting
please.
For this thing, just remember 3 things here, that it is important for the variance, the residuals are important for the normality, and the residuals are important for the case-wise diagnostic or the outlier also.
Yeah, ma'am. Dr. Poonam here, ma'am. Can you just repeat the standardized residual once again?
Yes. So standardized residual is basically if you take the mean of all residuals and if you deduct it from the predicted value. So the difference between the predicted and the mean of the residual, and if you divide it with a standard deviation, we call it as a standardized residual, right? Because why we are doing this standardization, remember the Z-score. We used to have a Z-score just to compare the 2 different units. So here we are using this standardized because we want to compare, not in this, but maybe when we will use the multiple linear, then we need that standardized residual also. Is it clear, Dr. Poonam?
Yes, ma'am. Yes, ma'am.
Okay. So now for the interpretation of beta coefficient, we see that the value, this beta coefficient, there are 2. We have seen that it is a beta 0 and beta 1. So that value of beta 0 is the y-intercept, and it is the mean of y for the population when the x is 0. So when the x is 0, this y will be equal to beta 0. The second is the value of beta 1, that is the slope. So it is the increase in, with the unit increase in x, what will be the change in y? That tells you the slope or the beta 1. And then third is we are interested to compare the predictors in terms of the effect. So basically, with this beta coefficient, we deduct a equation and we predict that. So if we come for this hypothesis testing, this null hypothesis says that this beta 1 is 0. That means coefficient of slope that is equal to 0. And this tells that beta 1 is not equal to 0. That coefficient of slope, it is not equal to 0. That is the alternate hypothesis. So coming to this steps, so maybe so first in the first step, you check the data for assumption 1 and 2, and both is the you do it with the continuous data. So it can be tested just by seeing the data. Then you run the chart builder to see the linearity, and then you run the linear regression commands. Then you basically analyze the result of, autocorrelation of residual that we will see. And then we do the case-wise diagnostic for outlier. In step 6, we check for the variance along with the line of best fit. That we do by the residual, which Dr. Neeraj was asking, and I'll explain each of these steps. And then ideally this residual should be normally distributed. And then in step 8, we interpret the R square. R square we have read regarding this in the correlation, that is the coefficient, this determination, the variance explained on the basis of this R square. And then we will write the table and make the table and write the interpretation. So now coming to this concept of homoscedasticity. So we have seen this homoscedasticity, and this homoscedasticity is a concept which is very much related to the variance. So the variance of residual, it should be constant across all the values of the independent variable. That means if you see this we check by the help of a graph. So this assumption of equal error variance, we check by the plotting a graph, where we plot a graph of, you can take it either unstandardized or standardized residual versus the unstandardized or standardized predicted value. So we know that this predicted value is known as the fitted values, which is the predicted value, and you check the residual whether it is varying or not. So you check the variance, and we know by the term variance, it is the square of standard deviation. So you take out the error. So how will you take out the variance of error? So if you can think that statistic concept, you will take the mean of all errors. You will deduct each individual error from that mean of error, and then you will divide it with the number of sample size. And if you square that, if you take the square it, that value will give you the variance. If you take the under root, it will give you the standard deviation. So this is the variance of errors. So this variance of errors, it should be constant across all the values of independent variable. And this we check by the plotting a graph. This is known as the homoscedasticity. So is it clear to all of you? How do we do that? Actually, how to interpret it on the graph, that I will show you. But theoretical part, did you understand that basically it is the residual variance? So the variance of residual, which Dr. Neeraj was asking, what is the utility of these residuals? So the first utility is that we check the variance. Variance means they should not be lying too much here and there, and it is told by a pattern. Like if you see, no, I think that graph is not there here.
Multiple.
Okay. So ideally, it should not follow. If you see that, I think that graph is not there. Let me show you that. Wait, that I have pasted in the multiple regression, but then you will not be able to. That graph is not here. Yes. So can you see these three patterns? So this, if the data doesn't follow this homoscedasticity, that data is known as the heteroscedasticity. So there will be, these three patterns will be observed. If you plot the graph of X and Y axis with the predicted and the residual, it will show you a plot which may show you such patterns. So here you can see that initially the distance from this X axis, it is very less, and then it is gradually increasing. Here you can see the distance is more and it is gradually tapering. Here you can see it is increasing more in initially, then decreased, and then increase. So there is some pattern which we call it as an increasing funnel, decreasing funnel, or fan shaped, right? So such patterns are observed if the variance of the residuals across the predicted independent variable is not same. And this is the independent variable. Remember, we have plotted the independent variable on the x-axis. So this is the independent variable. So the distance, the variance of this individual point, it should be constant across this independent variable. That is known as the homoscedasticity. So can you see, is it constant? No, it is very much increasing. And then it is decreasing, and this is fan shape. Okay. So this is the concept of this homo or heteroscedasticity. So is it clear? So now Dr. Shamshad would like to ask one question. You may ask.
Okay. In this graph, can you tell in which part of this graph prediction is good and in which part prediction is not good? In increasing funnel. Can anyone tell?
In the center,
In the later half or
in the later half, prediction is good or bad?
It is bad.
I think it will be in the center. It will be reasonably.
And in the
Center, it will be.
In beginning?
Yeah.
Part of this.
In beginning, the prediction is best because residual is less. That means कि prediction is very good with
see if the distance between these two now just to emphasize Dr. Shamshad's point, I would explain it. You can see these three graphs. So here, if the difference, if this is the independent variable, so this independent variable, the variance, it is not something like the distance residual, we were checking it against the fitted value, but here we are checking it against the independent variable. So here you can say that prediction is wherever you will make initially, since the dotted lines are very few. So even based on that few predictions, you cannot say that the model will be good, right? So that's the importance here, because the residual concept which you learned, that was between the predicted value and the observed value. This heteroscedasticity or homoscedasticity is between the independent variable and the residual. Okay, so did you understand these two concepts? So for now, just to make you clear, if you cannot see any pattern in the that plot, once you do this on the SPSS command, then you can appreciate it again. We can repeat the concept.
And just one more question.
Yes, yes.
So for this simple linear regression, we are just checking for the variance of the residuals and not of the actual data of the values that we have.
No, that also we do 3-4 functions.
That also.
Yes, I'm just telling you first the homoscedasticity,
which is checking for the variance in the residuals.
Residual against the standardized predicted value, which is the fitted value, because that predicted value, if you see the difference, then you call it like Dr. Shamshad was also telling you regarding the beginning or later. So nearer that point, closer to your fitted line, there it should be constant, right? So nearer the point, closer, like in this case, you can see you can see there are many points. So you can see that most of the, you can draw a parallel line here and here, and you can see that most of it has a constant from the predicted value. Okay. And if it is very much like initially it is very close and later it becomes very wide, then it will follow something of a, funnel type of pattern. Or initially it is very large and gradually it is tapering, then it will be like that the second type, right? So again, decreasing and increasing funnel. So that's if your graph is showing. So we check the residual, the distance of residual. That is again the same, something related to the outlier, because in outlier also you will be seeing that if it is very large value, you will remove that outlier, right? So this assumption of equal error we check by the residual against the predicted value, which is known as the fitted value. So is it clear up till this point?
Okay, ma'am.
Anybody else? So again, I think there was one more concept of autocorrelation. So the other concepts I will tell you once we see that graph, because without that you won't be able to visualize it, right? So I'll tell you. So now this is the example.
Hello, ma'am. I just wanted to ask one thing about this homoscedasticity, that it is basically the variance of the residuals constant across all the values of independent variable. So like variance between the residual and the independent variable we are getting, or the mean, that part I am a little confused.
It is the fitted value. It is a predicted value.
Okay.
It is the predicted value. Independent variable, I think I called that by mistake. It is the predicted value.
Okay.
Okay.
Okay, ma'am. Okay. Thank you.
So we have to use the appropriate statistical approach to predict the cholesterol level of subjects using the BMI of the subject and interpret the result. Okay. So this is the question which I have to attempt in the SPSS. So this is the data of SPSS, you can see. So now you can see there are data view and there is a variable view. In the variable view, you can see that there is ID, age, gender. One is female and two is male. You can see the values and the label just to know about the type of variable. This is very much similar to the previous one. So then the systolic blood pressure, diastolic blood pressure, serum cholesterol level, vitamin D level, and anxiety self-rating score. So all these are scale variables. Only two are the nominal variable, that is the gender and race. Okay, so this is the data. And this is data view, you can see these data. So am I audible now?
Yes, ma'am. Yes, ma'am.
Okay. So we have to go, and in the assumptions I told you that once we put a command, then only we can test about all those 4 assumptions. Okay. So I will tell you one by one regarding all these assumptions. So first we'll go to the graph, because we know that we have to check for the linearity. So I'll go to the chart builder. I'll click this. Here I have to click the scatter plot, select this, double click. So here there are 2 variables, the BMI and the cholesterol. So BMI will be on the x-axis and cholesterol will be on the y-axis. And then you can click OK. You can change that y-axis, but I have not changed that, but you can change that. So you can see that there is a sort of linear pattern. So that means one assumption that data should be linear. This is there. Now I will go to the analyze. You can see here there is an option of regression. The second option is the linear regression. Click on this linear regression. Dependent variable is the cholesterol. Independent variable is the BMI. I'll shift here, BMI. And then I will use these 2 options, statistics and plot. So if I come to the statistics, you can see here that this regression coefficient, This is the beta. So I need the confidence interval also, because this confidence interval will tell you the difference between the predicted means in the population. So this confidence interval I have clicked. Then the residual, we have to check. I have told you regarding the 3 functions of residual. The first function we did for the homoscedasticity. The second is on the basis of residual, we click this case-wise diagnostic, which will say that if the residuals are more than or less than 3 standard deviation, it will give you the separate table for those residuals. So I have kept a value of 3 here. By default, the SPSS takes this 3 standard deviation, more than 3 standard deviation as outlier. But if you wish your model, you can reduce this outlier, means this cutoff. You can put this 2, or you can keep this 2.5 also. But we keep this up till 3, because up till 3 it is okay. So up till 3 standard deviation, if any data is there, if it will keep that data. Otherwise, it will give you a table, separate table. That is the table of case-wise diagnostic, which tells you that the residuals are more than or less than 3 standard deviation. And this, we do one more testing with this residual. That is the Durbin-Watson test. This Durbin-Watson test is not every time needed. In most of the cases, it is not needed, because it is needed only when the residuals are very much correlated with each other, and there should not be a correlation between these residuals. That I'll explain you once we see the this Durbin-Watson statistics. Okay, so here we have to click these 3, and this model fit. This model fit, it is clicked, because it tells you about the equation which you are deriving, whether it is statistically significant or not. So press this continue, then come to this plot. If you come to the plot, then here you can see there are 2, you are driving a scatter plot. You can say this is scatter. Scatter means it also generates scatter plot, but it generates scatter plot between the predicted, Z predicted and Z residual. Z is basically Z score. So you shift this Z predicted to x-axis and Z residual to y-axis. So again, there is a use of residual here, because you want to check whether this value of residual, this graph we use for the to check the homoscedasticity. Remember, in homoscedasticity what we did, that you check the standardized or unstandardized value of residual against the predicted. So this, by this scatter plot, you do the residual, you do the checking of homoscedasticity, and then this residual again, this standardized residual, with this you do the histogram and normality. This is the PP plot, probability plot. Here we don't use QQ plot, rather we use probability plot, which is also one way to assess the normality. So are you clear why we are giving these commands? Or should I repeat it once again? So Priyanka is writing once again. Okay. Yes. Any other concept? So yes. So I will just cancel this. So first, this is, if you click this linear regression, this 2 window will appear. Dependent is cholesterol and independent is BMI. Now I have to use these 2 options, statistics and plot here, right? So if you click on statistics, you can see that there are 2 boxes here. There is one box of regression coefficient, there is one box of residual, and this model fit, it is automatically clicked. So I don't have to do anything here in this box. So here what I'll do, because I need confidence interval of my beta coefficient, so I will click this beta coefficient and this residual, because I have told you that this SPSS calculates the residual in the background. So I don't want any data to be there in my model where the value of residual is more than 3 standard deviation. So case-wise diagnostic will tell you, it will give you a output which will tell you that how far or how near that residual is after this 3 standard deviation. And this Durbin-Watson statistics, it tells you about the autocorrelation. Autocorrelation is between the, remember correlation? In correlation, what we used to do? We used to see the correlation coefficient between the two variables. If it is more than 0.5, it is 0.6 or 0.7. The value ranges from 0 to 1. So similar correlation, this SPSS checks with the residual. So this residual should not be very much correlated to each other. That autocorrelation should not be there. Because if there is autocorrelation, then one value of residual should not predict the other value of the residual. But this is not general with our data. This usually happens with the time series data. As for example, if you are doing a weather forecast means like aap dekhiga, you will see that you get a temperature these days, minimum maximum temperature or average temperature every day. So this will be very much near to each other. So in that case, it will be very much correlated. If you plot a correlation of like temperature or weather forecast, you are forecasting, predicting something that आप देखते होंगे ना, आता है कि भाई अगले 7 दिन में भी कितना टेम्परेचर होगा, एवरेज टेम्परेचर, सनलाइट क्या होगा, ड्यूरेशन क्या होगा. सो फॉर दैट वेदर फोरकास्ट देयर विल बी हाई collinearity, there will be high this correlation between the residual. So that correlation is known as the autocorrelation. But I don't want that autocorrelation in my data, because then it will hamper that model. It should not be there. And for that, I click that Watson statistics. But except for time series, most of the data we do now. Yes. So should I repeat it? Yes, I think I should, because I don't know from where I was not audible. So I was explaining the autocorrelation. So autocorrelation is generally, it is a phenomena which happens with the weather prediction or weather forecast, where the data will be very much closely related to each other. And in that case, maybe that if you do that residual thing, if you take the difference between the actual predicted value and the observed value, and each of these residuals may have got a high correlation with each other. So that will affect the prediction of the model, and you don't want that to happen. That's why you check with the, you click this Durbin-Watson statistics, and there is a value for it. We'll see how much should be the value of Durbin-Watson statistics. Okay. So now coming to the plot, because I have to explain. So press this continue. Coming to the plot. So remember in the homoscedasticity, what I told, that homoscedasticity, you see that the value of the residual, it should be the variance of the residual, it should be constant across all the values of the predictor variable. And for that, we plot this graph. So here will be a Z, that is a standardized residual. So this residual, we shift it to y-axis, and this predicted value, we shift it to x-axis. Okay. So this we do for generating a scatter plot. You can see it is writing a scatter. Scatter means a scatter plot for these two variables. And this we create for checking the homoscedasticity. And what is homoscedasticity? Homoscedasticity is the variance of the residual. It should be constant across the predicted value. Okay. And then we check the normality of this residual. So we check the standardized residual plot with the histogram. The continue, press OK, and then you will have a lot of output tables. So I'll explain these tables one by one. Okay. So the first, so are you clear up till this point? Putting the command, why we are giving those commands? Sukalyan is writing, repeating the previous one. So anyone who would like to repeat the concept or any command part, so please write in the chat box so that I could repeat those commands or concepts up till this point. Is it clear to you? Am I making some sense to you? Or things are, is it one way ANOVA? Okay. Yes, Arpan, actually what happens that model statistics, it gives you this ANOVA tells you the value of the significance of the model. It is not the one-way ANOVA, but this one-way ANOVA gives you the significance of the model, right? So it gives you the ANOVA value. Neeraj is writing in homoscedasticity graph, what is x-axis and what is y-axis. Okay. So remember, Neeraj, this x-axis, if you see the x-axis is always predicted value. This will be the predicted. I'll show you. So I'm coming down. See, this was the scatter plot which I clicked. Remember, it is a scatter plot, but the dependent variable is a serum cholesterol. And I have done a scatter plot with the predicted value on the x-axis and residual on the y-axis, right? It is a standardized residual and standardized predicted value. So you can remember that, oh yes, remember that, you know, P is, we always, this P is the independent variable because, sorry, it is not the predictor variable. So this is, no, it's a predicted value. Just don't go by that independent and dependent because it is giving you the value of residual. So this predicted will go, I remember it that P comes before the R and X come before the Y. So X on predicted values there on X and the residuals are there on the Y. Okay. Is it clear, Neeraj?
Yes, ma'am. It's clear. Thank you.
Okay. So then, so I will go again because I need to show you the results since beginning. So when you see that, you can see the command, it gives you the brief of the command also. You can see that, you know, it tells you the dependent variable method is enter, scatter plot, residual, Durbin-Watson, and case-wise diagnostic. So if you see this regression, it tells you that it has used an enter method of forming that regression equation. You will learn more about the method. There are other methods like backward method, forward method, enter method, that I'm not going into the detail for the simple linear regression because there is only one variable here. If there are multiple variables, then you may go for those type of methods, right? So if you see the model summary, so SPSS gives you the command like this. But before you see this model, you need to check for the other assumptions. So now that's why the other assumption, it comes a little down. So first I'll go down and this is for the normality. So this is the histogram. You can see here, this is the frequency and this is the histogram of residual. So Neeraj, now you can see that we check the normality also on the basis of histogram of residual, right? Because if the residuals are following normal pattern, then the assumption of normality is there. So you can see that the standard deviation is nearly 1 and this gives you the bell-shaped curve. So it is the histogram and this is the PP plot. So this is the PP plot of the, again, the standardized residual. And you can see that if it is follow approximately that along that diagonal line, then it is normally distributed. So this is the first function of residual, the standardized residual. We check for the normality and with the histogram of standardized residual also gives you the impression about whether the data is normally distributed or not. Then coming down, this is the scatter plot. So this scatter plot, remember this scatter plot between the standardized residual and standardized predicted value, this is to check for the homoscedasticity. Homoscedasticity was what? You check the variance of residual against a predicted value, gives you that, And you can see that it is not following any pattern like increasing funnel, decreasing funnel, fan like. It is not giving you. One can say that, it is like an increasing funnel if I draw a line here and here. But these data sets are very few in number. If you see the majority of the data, it is not giving you any pattern except that. And remember that pattern is only that increasing, decreasing and funnel. Most of the time, that heteroscedasticity will follow those patterns. So since it is not following any pattern, you can say that the variance of residual across this predicted value is constant. Okay, so this is the homoscedasticity. So that assumption is met. So remember, we have now checked 4 assumptions. We have checked for the normality of the data. We have checked for the linearity. We checked for the homoscedasticity. We checked that the data is both the continuous independent and the dependent is continuous. Now one is left, that is the outlier. So for outlier, I have told you that we have to go a table of case-wise diagnostic. So can you see here, there is a, so please focus on this table first. So this is a case-wise diagnostic table. So here you can see that 66, 154, 166, these are the case number where the value of this standardized residual, it is more than 3, right? You can see it is 3.066. It takes the up till 3 decimal point. So here, if you want to remove which variable you, and it shows you the serum cholesterol level, it shows you the difference between the predicted. I mean, the difference, you can see that this was the actual and this was the predicted. So difference between this and this is how much? This is minus 152. Can you see? Like some Biraval was asking now that why we will do the difference, but we will not do the difference. The SPSS does it in the background. So you can see it is giving a residual to all the values. So all these, if you imagine all these cases. Yes.
Yeah, Poonam ma'am. Ma'am, I think there is some connectivity issue from your side, ma'am. In between, like we are unable to hear you, ma'am.
Okay, so from where I should repeat? I'll repeat.
Case-wise diagnosis is fine, ma'am. But it is happening regularly, ma'am. Like we are.
Is this phenomena is being observed by any?
Not right now, ma'am. Not with us.
Oh, so if it is not with the other participants, Poonam, can you check your internet connection? Because had it been from my side, it would have been same for all the participants. Because if it is differential, then I think you need to check a little bit.
Okay, ma'am. Okay, ma'am.
And if you feel this, please text in between. I will repeat the concepts, and you will get the videos also if you have not able to listen or you have missed out on something. Ashish is also writing. Ma'am was not able to hear. Okay, so just then I'll repeat the concept. Just guide me from where I should repeat. I'll repeat. So should I repeat the commands or should I repeat before the theory part also? Ashish and Poonam, or any specific thing which you want me to repeat? Please. Also, Priyanka is writing interpretation. Okay, Priyanka, case Ashish is writing case-wise diagnostic. Okay, so I'll repeat once again from interpretation. So I'll escape this and I'll go above. So are you guys okay with the commands? How we are giving the commands? Which options are we using? Are you guys okay? One of you, if you can text okay, then I may proceed. So Ria is writing yes, no, not Ria. Anybody outside the AIIMS? Priyanka is writing yes. Okay. Ashish, Shruti, everyone writing okay. So okay, so if you have understood till this command, you see this regression. It tells you this table tells you the method which it has used while giving that beta coefficient or that regression equation, and the method used is enter. So this method is used for a variable where there is only single variable. There are many other methods also, like forward, backward. We will learn more about that in the multiple linear and logistic regression. But since here there is only single independent variable, it takes this enter method for giving you the regression equation. Is it clear up till this point? Priyanka and Poonam and Ashish?
Yes, ma'am.
Okay. So now coming to this model summary, yes, no, I'm not discussing the model summary now, because first I have to check the assumption. Then only I will say that whether I should be able to interpret my model or not, right? So I will, but the SPSS doesn't give this output in sequence. So it is a bit haphazard. That plots, it comes in the last, and that table it generates first. So you need to go down. So I'm not seeing, just you can, in between you can see that the value of ANOVA, it tells you that it is significant. But this also I don't want to see now before I check my assumption. So I'll go down and I'll see this graph. So this is the normality. You can see this is the histogram of the standardized residual. And this tells you whether your residuals are normally distributed or not. So in the other part of the basic statistics, you were checking for the normality of the raw data. But here we do not focus on the raw data. Rather, if you ask from the standard statistician and the standard textbook, they say to check for residuals there in the ANOVA also. But there we have not used that because we thought that it will go a bit complicated. So that's why we have not introduced the concept of residual that time. Residuals, basically the concept comes when we are making predictions. So that's why if you do this normality plot of residuals, and if it is normally distributed, that means that the data is normally distributed. So for that we do this histogram with the this bell-shaped curve, and then we see this PP plot. So PP plot is the probability plot, and this tells you about the linearity of this tells you about the normality, not the linearity. Linearity we have checked with the scatter plot. Remember, in the first thing, in the chart builder, we used to see whether the data is linear or not. We have used that option of the scatter plot. So now if you see this, then this is the scatter plot, and here also you can see with this scatter plot also that it is we see basically the homoscedasticity. Homoscedasticity is the concept where we check the variance of residual against a standardized predicted value, and when you plot the graph between these two, this shape of the graph or shape of the points, it tells you whether the data is following homoscedasticity or not. And if there is no pattern, then you can say that it is a following homoscedasticity. And the pattern could be, I've shown you that basically 3 increasing funnel, decreasing funnel, or fan shape. So here it is not following any pattern. So we can say that the data, it is following homoscedasticity, means the variance of residual across the predicted value is constant, right? Now the third comes the outlier. For the outlier, we see this list of case-wise diagnostic. So in the case-wise diagnostic, if you see this, please focus on this table first. Yes. So now I would like any one of you to explain this table for me, for whom I was audible. Yes, Ria, can you explain this table to everyone? Am I audible, or any one of you?
Yes, ma'am.
What the various columns of this case-wise diagnostic is showing?
Yes, ma'am. Basically, the case number is showing the number.
You can explain with one, like you can explain with case number 154.
Okay, ma'am. Case number in the case number 154, the predicted value of serum cholesterol is 276.261, but the observed which came each is on a data is 124. So
Okay.
If we subtract the observed, subtract the expected, that is a predicted from the observed, we are getting the residual, the unstandardized residual of minus 152.2606, that is represented in the final column. And if we are standardizing it in terms of the standard deviation, then we get minus 3.065, which is in the column of standard residual.
Okay. So now, and if you just interpret this standard residual column, so can you say which two case number are having the highest standardized residual?
Ma'am, the highest standardized residual is in the case number 186, that is minus 3.688, and there is 162 case number, that is minus 3.704. It is outside 3 standard deviations.
Yes, thank you, Ria. So all the case number which it is showing, it is outside 3 standard deviation. But if you see the rest of one, that is 3.0 and then something. But in this case, in both these case number 162 and in case number 186, and if you see their values also, you can see that the predicted value is too high. Like Dr. Shamshad was giving an example now, that if the student has expected that out of 100, I'll get 99 and he got 50, then see the gap between the expected and and the actual. So you can see that the actual cholesterol was 123, but predicted was 306. That is too high. Rather, if you see all these levels, it is in hundreds and it is in this thing. So just if you see this unstandardized residual, it will be difficult for us to interpret. That's why this SPSS statistics, it converts this unstandardized residual into a standardized residual, because on the basis of this, we can remove. How will we take the decision on the basis of this unstandardized one, that whom to remove and whom not to? So if you convert this in the standardized one, then we can compare, right? Because it is in the single 1, 2, 3 standard residual, then it is easy to compare. That's why. So now you can see that this case-wise diagnostic, that this gives you the value of the residuals in the form of standard residual. And it is up to you whether you want to keep these data or you want to remove this. So the total number of study sample size in our case is 193. So either you can take the decision to remove all, or either you can take the decision to remove these two extreme, like 186 and 162, because that is very high. And the other are like up till 3, a little bit away from 3. Right. So is it clear to all of you? How to diagnose this case-wise diagnostic?
Dr. Pragya, if we want to remove some data, how do we remove it actually from the main data sheet?
Yes. So what you do, save it with another. Don't remove the main data sheet. Save that same SPSS with some other name. Maybe that, final analysis. And then remove this. I have shown you, like, if you want to remove this, मान लीजिए case number 186 हटाना है. So you can go यहाँ से, you come down. This is the case 186. Right. And you can press this delete from here. I'm not pressing it. Otherwise, there is a cut, there is a clear. Can you see this option of clear?
Yes.
You can clear, but have that main data set with you. Whatever you want to delete or not delete, do it on a separate file, which you save it, because you might need that actual data set for some other analysis. Because, outlier keep on changing with the type of analysis. Maybe this 186 will not come with some other number, right? If you are doing one-way ANOVA, or if you are doing some other test, then maybe this will not come, right? So if you keep on deleting on the main file, then it will have problems. So you can save this with some other name, then delete this, and then re-perform all the commands, right? Just after deleting, you cannot go with the same output, right? You need to put all the commands of fresh and then write the analysis. Is it clear, Dr. Kamlesh?
Yeah, it is.
Okay, yes. And so any other questions up till this point? So now, is it clear to all of you now who were having this problem of predicted and actual? So you can see for every actual value, this SPSS predicts based on some calculation, regression equation. So this is the predicted value, and the difference between these two gives you the residual. And when you standardize that residual for comparison, it is known as the standardized residual. And on the basis of standardized residual, you can take the decision to include that particular case number or to remove that particular case number. If you take the decision to exclude that, again, then you can remove all these case number, and you should reperform all the commands, come with a separate output, then enter the data in the table, and then write the interpretation. Is it clear up till this point? Then I'll move forward. Otherwise, I think Ashish. So you asked for a case-wise diagnostic. Is it clear to you now?
Yes, ma'am. Yes, ma'am.
Okay. And there were two more participants. Poonam, yes, so clear?
Yes, ma'am.
Okay. Ma'am, is there any broad objective, Neeraj, to decide? So Neeraj, is it clear now?
Yes, ma'am, it's clear, but I just want to know, like, here it's our arbitrariness. Sometimes we are going to take anything above to make it more robust, or anything above.
That is up to you. That is up to you. That depends on the sample size also. If the sample size is very huge, very large, you can write, up to you. You can take more also, because then it will not affect. So it is up to you. The main thing is like, by default, we keep it up till 3. And that concept of sample size also comes in that we will do in the multiple linear regression, and the logistic also. For each variable to be in the independent variable, there should be at least 50 sample for each variable. Like if you are taking the number of independent variable as 10, then 50 multiplied by 10, 500 samples should be there for that model to be very much predictable and good. Many people say it should be 15, it should be 20. But we recommend that at least it should be 50. With a sample of 60, with a sample of 100, taking 7-8 variable, you cannot make a good model.
But usually when we are going to use prediction models, the research question will be, in the beginning, the research question will be entirely different. And there the sample size calculation will be based on something else, and then you decide that it may happen that the primary outcome, it may be the secondary outcome, so you are doing more of a post analysis or exploratory analysis where this sample size will not be feasible, because your sample size was decided a priori based on that primary outcome.
Yes, it happens many a times that you did not decide in the beginning that you have to do a prediction. And your
You are not audible.
Okay. So
now again you are audible. Yeah.
Okay, so I was about to tell you, yes, you are very right, that if you don't start with a research question entirely based on prediction, then you may have to face this problem that you have decided later on as a secondary objective. Then in that case, we would recommend either you don't make a model, or if you wish to make a model, then do it, but simultaneously in the limitation, you may mention that your sample size was not adequate. So maybe that model which you are suggesting, that is not going to be very much generalizable, right? So
and
that you can, yes.
When we look at the normalcy of these residuals, are we going to look at because you showed both histogram and PP plot as standardized residuals, no?
Yes.
Normalcy. So are we supposed to use standardized, unstandardized, or both, or it doesn't make any difference?
Generally, the option which that gives you, it gives you the standardized one. So it tells you that you should check the value of that Z score. That's why that Z residual, it comes in the option. If you click this option, SPSS, I don't think it gives us the, if I just, let me check this because I have not checked this. Maybe linear, if I check this, just a sec. You can do both, I think, standardized or unstandardized. If you
it doesn't make difference. Means you have to see either.
Yes, I think so. But if you see this is all. I think all this scatter plot for normality. This gives you these values, no? So no, this is for this thing. So
this is for homologous.
This is standardized only. It doesn't give here that unstandardized. By default, the SPSS has not given you the command to plot a normality for this unstandardized.
So is there any objective way also, like apart from looking at the graph?
Yes.
The value which it gives so that one can take a call that is it normally distributed?
No, it is it is not something like that. Like we did in the basic one. In basic also, it was only for sample size less than 50, that Shapiro-Wilk, where that p-value you could check. But for the larger sample, we always told you that you should use QQ plot. Right. Okay. So it is subjective.
Thank you.
Yes. So if it is okay up till this point, then may I go for the other part of the interpretation? Someone has to say yes. Okay. So if you are okay up till this, then I'll go above. Now I have checked for all my assumption and I have decided that I will not remove this data just for practical. You may remove it, up to you. Whatever is the case, you may report it. So you have written this and then I have checked all this and then now come to the model. So if you see the model summary, you can see that this R square, there is an adjusted R square and this R square. So R square, you read about this in the correlation. This tells you the variance or the coefficient of determination. So you multiply this by 100 and that means 16.2% of the variation in the cholesterol can be explained by the change in BMI. That's the interpretation of adjusted R square. And this is the Durbin-Watson statistics. So you can see here, the value of Durbin-Watson statistics is 1.9. It should be close to 2. So if it is close to 2, it is 1.8. That means there is no autocorrelation of residual. And autocorrelation, if you can recall, what we did, that the residual should not be correlated. And that is usually there only with time series data, like weather forecast. Otherwise, normally it doesn't happen. So even if you don't wish to put this command, it is fair enough. Because if you don't expect your data to be something like a time series data, you don't click this command. And then comes this ANOVA. This ANOVA gives you the significance of this equation which you have taken. So this gives you the value of ANOVA, the 2 degree of freedom, that is the 1 and 92, and the significance value, that is the 0.00. So this is a significant model which you are going to tell, or then comes your actual this coefficient. This is the most important part of that we did the simple linear regression. So based on this table, it tells you the equation, right? This one, coefficient, because this gives you the coefficient and it's 95% confidence interval. This 131 is the intercept, that is the constant. So this 131 is the constant, and this is the beta coefficient of BMI, and this is the significant value. So if you want to make an equation, what equation you will write? You will write that the value of cholesterol is equal to 131.65 plus 4.2 into BMI. So is it clear to everyone? I'll show this it is there in the PPT also, but did you understand how we make the equation? So you write Y, that is the cholesterol, is equal to that 131, that is the constant, plus 4. Oh, it's not clear. Ashish is writing, it's not clear. So, okay, then I'll go to the, so this, Ashish, is it clear? If you can recall that equation, Y is equal to beta 0 plus beta 1 into X. Can you recall that? Or I will open both.
Yes, ma'am. Yes, ma'am.
So that beta, that constant is, yeah, someone is writing, could you repeat Durbin-Watson? So Durbin-Watson is, again, I said that if it is value is more than, if it is close to 1 to 2, then it is, the data is not autocorrelated. So then the second is your this coefficient. So it is basically, who is writing this adjusted R square? Neeraj. Oh, sorry. This R square is on your sample data, and when you project that in the population, it is the adjusted R square. So I forgot to clear that. So R square is the sample, adjusted R square is the population, right? So ANOVA table, okay. So ANOVA table is if you can recall ANOVA, we express the ANOVA, the result of ANOVA, by its value F, the two degree of freedom and its significance level. So this is the 2 degree of freedom, that is the 1 and the 191, and the value of F is 38.09 and the significance is less than 0.05. And this all you will see in the interpretation section, how to write the interpretation. I'm just explaining you, and then like we did for the basic, here also you will see how to enter the result in the table and then how to write the interpretation. So is it okay? So now coming to this coefficient, this is the formula. This y is equal to 131 plus 4.28 into body mass index. Okay. So now coming to the interpretation. So I'll open simultaneously both these things. These all commands are there in your PPT. Everything is there. Whatever I have shown you, everything is there in the PPT, in the stepwise this thing. So you can refer to these things later on also. So it is there, yes. A few things are extra. So now coming to the interpretation. So this is the linear regression. So this was the problem statement. So now you can see here, I will simultaneously open these two, this one and the output, so that you can see. So here you can, I'll just minimize this a little bit. So can you see this? Is this table visible to all of you? And can you see both the screens simultaneously? So now you can see that I have.
What is the importance of constant?
This constant?
Yes, ma'am.
This is the equation, Ashish. Let me give you, yes. This cholesterol concentration. Because now you calculate, this is my equation. Can you see this one? So now what is your BMI? I don't know what is your BMI. Like if your BMI is, let's say you are 22. So please calculate what will be your cholesterol concentration. Do it on the calculator. Ashish?
Yes, ma'am. What should I take as a value of BMI?
22. I said that I'm assuming you are 22. Your BMI is 22. So if I am taking your BMI, no, prediction is something like that. You are doing individual prediction. So if my equation is this, then what should be your cholesterol level?
I'm solving right now.
All of you can do this. So Veeraval is writing 226.2. So yes, it's 131.6 plus 4.3 into 22. And then you add both the two. So they are writing 226. So that's the predicted value of cholesterol. It's not the actual.
So to simplify,
Yes.
if I am correct, no one is having cholesterol level less than 131. So everyone is having his cholesterol level above 131.6. That is why
131 plus. अगर इसका intercept 1 भी होगा, तो BMI का 20 या 18 तो आएगा ही. Plus some BMI का value.
हाँ, plus some BMI का value.
Yes.
So ये जो beta 0 है, that is for the x is equal to 0 value, right?
No.
Beta is not 0 here.
No, Dr. Kamlesh. You can't do like this. You put the BMI 0. There is no BMI 0. Listen, you have created this equation on a data where everyone has some BMI. In that case, you will use this equation for those BMI data range only. You cannot put BMI 100 and find a cholesterol. Remember, if your data has a BMI range from 14 to 28 and you derive this equation from this BMI, then you can use this equation for those BMI also. Imaginarily, you can put BMI 1000, you will get a cholesterol level.
I just wanted to tell that if we are plotting it on X and Y, so if we extrapolate.
No. Extrapolation is not possible.
Okay.
Extrapolation is not applicable.
Means it is just the one thing like you can say that if you, why, first tell me why we are doing such predictions. I think then you will be able to answer this, Dr. Kamlesh. Why do you want to predict cholesterol?
Yeah, so that without actually measuring cholesterol, we can get some idea what the cholesterol could be there of a person with certain BMI.
Yes, like we have made the WHO, there are many predictions based on cardiovascular risk factor. If you are this, then your risk is this much. If you are so there are many practical things also, like you will see that we predict the age of weight of that is very commonly done in the pediatrics. That if what is your age, and based on that I can predict your weight, right?
True.
That is also a type of linear regression, also simple linear. कि सिर्फ आपने age आपने बच्चे का पूछा और आप बता दीजिएगा age into 2 + 8, something like that, right? So it is something of that sort. And this, I mean, your question was like, you will keep this 131 fixed because that's a constant here in the equation.
Yeah, ये जो constant उसने निकाला है, वो ऐसे करके निकाला है कि इससे कम किसी का नहीं आएगा, चाहे इवन BMI अगर 0 भी हो, मतलब hypothetically,
क्योंकि वही तो that's the concept ना शुरू में हमने देखा ना कि that intercept is the value of y when that coefficient of the other variable is 0.
Exactly, वही मैं बोलना चाह रहा हूँ.
बिल्कुल सही बोल रहे हैं आप.
It starts from that point itself.
Yes. That's how we define this intercept.
Yes.
That if the value of beta 1 is 0, then the value of y will be equal to the intercept.
Intercept, yes.
Is it clear?
Yeah.
Okay. So now I think this is the table. So can you see this? This is a constant. This is, again, I have entered this one. This beta I have entered here. I have taken this 95% CI also because that is needed. So the 95% CIO, this constant may range from 94 to 168, and this may range from 2.9 to 5.6. This is the value of T, and this is the P value. And here you can write the R square, adjusted R square, Durbin-Watson we have given, and this F is giving you the model summary, that whether your model is significant or not. Here I have included this F value. In the bracket, I have written the 2 degree of freedom of this 1 and 191, and I have written the this P value. Okay. So now if I go down, this is the way you will write your, and then you may write your interpretation.
So ma'am, we are taking P value of the ANOVA table only. P value, yes.
Yes, here you will have to take for the model, if your model was significant or not. That you get from the ANOVA table.
Okay, ma'am.
Okay. Because every table is telling you something different. So this table is telling you the variance explained, and that everything we have written here in the interpretation. So one of you, please read this for me. So I'll enlarge this. Then it will become easy. I will. Yes. So who will read?
Ma'am, linear regression was run to understand the effect of body mass index on cholesterol concentration. A scatter plot of cholesterol concentration against body mass index was plotted to assess linearity. Visual inspection of these two plots indicated a linear relationship between the variables. In addition, there was homoscedasticity and normality of the residuals.
But I will write here the predict, because
to predict, yes.
Predict BMI, predict the effect of BMI. Yeah, you can write here the predict the cholesterol level
from BMI to.
Yes. And then
the prediction equation was cholesterol concentration is equal to 131.6 plus 4.3 into the BMI, the observed BMI, which we'll be getting. BMI was statistically significantly able to predict cholesterol concentration. F value is 38.1, degree of freedom 1 and 191. P value was less than 0.0005. And this accounted for, there was 16.6% of the variation in cholesterol concentration with adjusted R square was 16.2%. This was a medium-sized effect according to Cohen. Okay. 1 unit increase in BMI leads to 4.3 millimole per liter increase in cholesterol concentration. Ma'am, ये Cohen वाला समझ में नहीं आया.
Ma'am, similar question like Cohen, why it is called medium
Cohen,
size, and
we
then
had
what is
read
the
about Cohen kappa, I think.
why medium size?
Actually, yes. That's why I was discussing it with Dr. Shamshad. This we should not have included because we have not told you, right? So actually, this is a reference of one person, Cohen kappa. So you may delete it, right?
If
Yes.
anything is
Now, please continue.
Okay, ma'am. BMI was able to statistically significantly predict cholesterol concentration, F value 38.1 and P value was 0.005. This accounted for 16.6% variation in cholesterol concentration with adjusted R square 16.2%. 1 unit increase in BMI led to 4.3 millimole per liter increase in cholesterol concentration.
Yes, and I think Veeraval will tell us what we have missed out here.
Ma'am, I just want to ask one thing. Suppose the result did not come significant.
Yes.
So then what changes would be in the interpretation?
Then you can write that it was not significant, the way you write it for the other result.
Okay, so then we can write BMI was non-significantly predicted cholesterol concentration.
Yes. You tried making the model, you tried predicting it, but it is not significant. Maybe you need to do it with more sample size, or because many a times if the sample size is not adequate, it will not give you a good model.
And ma'am, for the rest also, like the first.
Can you write 1 unit increase in BMI leads to 4.3 if it's a non-significant?
No. Then you cannot. If it is not significant, then you cannot interpret it.
Okay, we cannot interpret it. Okay,
you should not. I mean, you can, but you should not.
Ma'am, so the p value is not significant, so I cannot do that equation. So that equation is no longer valid.
It's not a significant predictor.
It's not a significant. You can write that it was the equation was this, but it was not significant. So then everything stops here. That point.
Okay.
And the first assumption of linearity, if that is not fulfilled in any way, we will not be able to progress with this. So
there are other ways like partial regression plot, and there are other ways to solve that. But we are not going. It's better to have more samples because that problem comes when you have got less sample size.
So for linearity, it is best to have greater samples.
Yes, then definitely it will be linear.
Okay, ma'am. And for the rest, like last time we had read about the accommodations that we could make in case it was not normally distributed or there was no.
That was non-parametric.
That was not. So if we find that our residuals are not normally distributed.
Yes, then if they are not normally distributed, in that case, there are ways to handle that. But in that case, it's better,
to remove the outliers.
Yes, you perform again the analysis.
Okay, ma'am. Similarly, for homoscedasticity also, there is no other value to take. Like last time for Levines, we were taking some other value.
No. That is not there in this case because it's the prediction. So the alternative, there are other ways to do it. The other methods to do it. There is that I told you least square. There is a least square regression. So those things are there. But with linear regression, you cannot do. There are other ways of regression. That is there is a partial least square regression. There is a least square regression where we convert those variable like for non-normal data. We told you that you can do a log transformation. So here you can do a lambda. There are many lambda, delta, so many transformation you can do. But that is
ma'am.
तो हम वो ज़्यादा हो जाएगा because that itself is a huge topic. How to do that lambda transformation?
ठीक है ma'am.
So it's better. If you need so many statistical tests to make your data normal, that simple conveys that your sample size is not adequate.
Right. Okay.
Right. So rather than putting those statistical tests, it's better you increase your sample size.
Ma'am, can you project your output file, SPSS output?
Yes, sure.
Here, ma'am, I just want to know if you can just, in the constant part, the significance value is coming less than 0.05. So suppose if your ANOVA gives you a non-significant result. So will these sig will be significant in that case or not?
No, I don't think so. If ANOVA is not significant, then so this will not be significant. But I have not checked it. Means I'll have to see a reference before commenting or before saying anything. But that is my normal sense, which is saying that if it is not significant, then it should not come. The coefficient should not come significant.
Ma'am, we have to progress to the coefficients only if it comes significant.
Yes. Only the model is significant. But for this answer, I'll have to check. So, Dr.
Ma'am, can we try with the other variables? We have so many of the variables in our table.
I mean, we will do it in multiple linear, na? That is the next session.
Right now, for just any other, we have taken BMI with this.
Just for practice.
Can we take
in practice session you have
height with cholesterol?
ले सकते हैं वो आपका है next the exercise में कुछ different ही दिया हुआ है that you can practice in the breakout room. So this I am not sure at this juncture whether if the ANOVA is not significant, whether this coefficient will be significant or not. But I will refer few good articles and then I'll get back to you tomorrow for this question.
Sure.
Okay. Any other query before we move to the breakout room?
Ma'am, मेरा question था कि like how much R square value would we consider it to be good or
more than 10%. वो उसमें एक्चुअली है ना अलग अलग उसका जो कोहेन ने इसको क्लासिफाई किया है लेस देन 10 से आई थिंक 30 या कुछ है और उससे ज्यादा है सो अबव 10 इज अ मीडियम सो यू कैन टेक इट एज अ
ओके मैम एंड 30 के ऊपर हाई
ऊपर का कट ऑफ मुझे याद नहीं है इसलिए उसको 30 के ऊपर मत बिलो उसको भी मैं एक बार चेक कर लूंगी
ओके मैम
10 से ऊपर अच्छा है मीडियम है
ओके
मैम वन बेसिक क्वेश्चन ये जो सिस्टम SPSS software when it makes this line best line of fit so to me it seems that the computer must be making thousands of such lines and out of that it must be picking the best line.
Yes.
So what exactly the computer or the software does in the background?
The graph actually when you plot a graph you have to click line of best fit. So definitely you are right.
That I agree, ma'am.
Yes.
I just want to know what is going on in the background in the software. What exactly is happening?
It takes you that which is the predicted one, which gives you the best least distance. All that assumptions you read now that it will have a least residual, the normality that will be least as compared to all other graphs, right?
Hello.
That
because we are lacking time, we can explain, but we are behind time.
Actually, we will explain it. ये ग्राफ यहाँ जो ग्राफ है ना, इसमें अगर करके आप करोगे तो वो आ जाता है. That multiple line will be there. You can keep on changing the line.
मैडम बस कल एक बार ये बता दीजिए कि वो लाइन कैसे हम लोग कहाँ से लेते हैं वो कमांड बेस्ट फिट लाइन का.
लेकिन चलिए ठीक है अगर आपको अभी जानना है ये एक कमांड उसमें एक्चुअली मेरे उससे नहीं आता है. एक मिनट जैसे सपोज BMI है एक मिनट रुकिए मैं आपको बता रही हूँ मोर हाइट फ्लोटिंग देन दिस इज ओके ये आपका आ गया. इसको आप डबल क्लिक करेंगे जब व्हेन यू डबल क्लिक दिस स्कैटर प्लॉट यहाँ पे आप देखोगे ना एक एलिमेंट्स है. एलिमेंट्स में आ गया फिट लाइन एट टोटल राइट. तो इसमें आप अगर ये करेंगे क्लिक तो एक आपको ये बेस्ट फिट लाइन दिखाएगा. ठीक है. इसमें भी फिर ऑप्शन है वो ऑप्शन एक्चुअली फिर इसमें एक प्रॉपर्टीज का ऑप्शन आता है जिसमें आपका ये और अगर आपको इसको पब्लिश करना है सो यू हैव टू रिमूव दिस ग्रे कलर एंड ऑल एंड लाइन. सो देयर आर फॉर्मेटिंग ऑप्शंस so that we will show you in the multiple linear. लेकिन ये जो ग्राफ के ऑप्शंस है ना जब भी आप डबल क्लिक करेंगे ना इसमें आपको बहुत सारे ऑप्शंस दिखेंगे. देख लीजिए यहाँ पे y एक्सेस है, टाइटल है, एनोटेशंस, टेक्स्ट बॉक्स है, ट्रांसपोज है, तो बेसिकली हम लोग ज्यादा यूज करते हैं एड फिट लाइन टोटल, ठीक है, ये बेस्ट फिट लाइन एलिमेंट से जाके करते हैं, इसको भी ग्राफ को भी चेंज करते हैं जिससे वो कैसे पब्लिश हो। ये आपको हम लोग कोशिश करेंगे सिंपल मल्टीपल लीनियर में, बट अभी तो 12-20 हो गया, आई डोंट नो हम लोग कैसे करेंगे, वो तो और भी लंबा है। तो अभी के लिए आप पहले ब्रेकआउट रूम एक बार प्रैक्टिस कीजिए, जो कुछ पार्ट रह जाएगा उसको हम लोग नोट करेंगे, और वो ऐसा होगा तो आपको बता देंगे अलग से, ये सब भी बता देंगे आपको, ऐसा कुछ नहीं है, बट ये सेपरेट इसमें ना फिर 5-10 मिनट लग जाएगा इसके पूरे फॉर्मेटिंग को करने में, बताने में।
ठीक ठीक, थैंक यू
मैम। एक लास्ट क्वेश्चन, ये जो आपका इक्वेशन आ रहा है इस समय बॉक्स के, y is equals to 1.32 E2. Equation was 132 plus 4.28 into x. तो ये E2
ये E2 वो उसमें मुझे लगता है ये E2 क्यों दे रहा है ये मुझे भी नहीं इसमें पता है।
I think it is log transformation.
E2 means multiply by 100.
That I agree, multiply by 100, but E2 क्या है?
तो ये 130 हो गया ना, अगर 1.32 into 100 हो गया तो 132 हो गया।
नहीं हो गया, बट ये E2 है क्या वैसे? वो तो एग्री
10 to the power 2.
10 to the power 2. It is expressed, आपने देखा होगा p वैल्यू भी तो ऐसे करके आता है, e करके, रिमेम्बर अगर बहुत बड़ा होता है ये e is 10 to the power 2, e is 10 and e2 is 10 to the power 2, so 1.32 is 132.
Okay.
Yes. Actually log transformation है शायद।
Yes, आप अभी के लिए उतना समझ।
Okay, breakout room.